In the last section, we finished up a little refactor of our application. We now have exactly one child in our cluster. Make sure you've only got one cluster.fork right here. And that one child has just one thread available to it. We're now going to start running some benchmarks on our application, and I'm going to show you where you start to get diminishing returns by increasing the number of children inside of your app. So let's get to it. I'm going to flip back over to my terminal, and I'm going to make sure that I restart my server by running node index.js. And then I'm going to open up my second terminal window where we're going to do a little bit of benchmarking with that AB command. So over here, I'm going to first start off by giving us kind of a baseline. We're going to say that when we have one child with one thread, how long does it take to process exactly one incoming request? So I'm going to say AB-C1-N1. So that means make one request with a concurrency of 1. Let's just establish a baseline here. And I'll say localhost 3000 /. We're not using fast here because remember the root route is what is actually triggering the hashing function call. The other thing I want to mention very quickly here is make sure you get on this / at the very end. For me personally, Apache benchmark breaks if I do not include that /. So I encourage you to add it as well. Okay, so let's run this and see how long it takes to run exactly one hashing function call. Okay, so it runs and I see about, 1 second, very similar to what we had seen previously when we did some very manual benchmarking of our application. So I'm now going to change what's going on here a little bit. I'm going to make a very subtle change, okay? It's going to be very, very subtle. And it's going to be kind of challenging to understand the results exactly, but we'll walk through it together very carefully and you'll get a really good idea of what's going on. I'm now going to change the concurrency. Actually, let me clean this up so you can see everything. I'm going to change the concurrency to be 2, and I'm going to change the request count to be 2 as well. So now we are making 2 requests at the exact same time to our one child inside of our cluster. And that one child has exactly one thread available. So let's run this and now see what happens. Okay, we're waiting, and then we get some results back. So now, in this case, we get some results that are kind of challenging to interpret at the very start. Okay, let me walk you through this. You'll notice that it looks like the vast majority of our 2 requests, it says, basically all these right here, took about 2.1 seconds to be processed. But if you look very carefully, you'll see that we have a minimum request time of 1 second. So out of those 2 requests, one request took 1 second to complete, the other took 2 seconds. So let's take a look at a diagram that's going to help explain the result that we're seeing right here. And then we're going to be able to extrapolate this to some of the larger cluster sizes and see where our performance starts to drop off. Okay, so this is what we just ran a second ago. So this is what's happening. We have 2 requests coming into our server to run that pbk-df2 function. Now the instant that the first request comes in, and remember they're being issued at the same time, but essentially one of those is going to reach our server before the other, that very first request immediately gets picked up by the thread pool and our server starts to process it. As soon as that first pbk-df2 function is complete, our server responds at about the 1 second mark. And that explains the minimum response time right here of just about 1 second. Now at the same exact time, that second request comes in as well. The way I've put together this diagram is a little bit misleading right here. So technically, the second request comes in like at time equals 0 as well. But this diagram that I'm showing you is meant to give you an idea of when the actual processing in the thread pool occurred on the second pbk-df2. So we finished up the first hash call at 1 second, and the instant that one was complete, our server then started to work on the second hashing function. That took an additional 1 second, and so it eventually sent back the result at 2 seconds. And that explains the 2.1 second that we see right here. So the first call took about 1 second, the second call took 2 seconds. And yes, they occurred at exactly the same time. But our server only has the ability to process one hashing function at a time because we restricted that thread pool size to exactly 1 thread. Okay, so at this point, you're probably thinking, Stephen, where are you going with this? I understand it, whatever, get to the point. Okay, just bear with me. This is like gonna come together very, very nicely, all right? Just a little bit longer. Let's get to it. So we're now going to look at a second condition here. We're gonna try running clustering with 2 children and see what type of response time we get now. So back inside my index.js file, I'm gonna copy paste down cluster.fork. I'm then going to go restart my server. So I'm gonna kill my server and start it back up. And then I'm going to run my benchmark one more time with the exact same parameters. So 2 requests, both at the same time. In this case, we have 2 children running. So I'm gonna run, and then I get the result back, and it only took about 1 second to process both those. So I have a minimum of 1161 and a maximum of like 1171. So definitely these 2 requests very clearly have been processed just about in parallel. They both came in. Clearly, one child inside of our cluster picked up the first call and started processing it. And then the second child inside of our cluster started processing the second one. They both completed at the 1 second mark. We sent back the response and everyone was happy. So by using clustering, we very clearly, like no 2 ways about it, by using clustering, we have gotten a very distinct benefit here. Before, it took 2 seconds to do this work. And now by using clustering, it took us 1 second. We cut the time in half and we should be really happy, right? So you might be thinking, hey man, this is great. Let's just keep increasing the number of children. Let's fork this process a whole bunch. I'm gonna take it all the way out to 6. So I've now got 3 here, 3 here. Whenever we start up our application now, we're gonna get 6 separate instances. And these 6 separate instances can all be used to process incoming requests, and everyone is going to be served a response back even faster than before. Or at least that's what you might think. Okay, that's not what's really going to happen here. So let's save this file. We're going to restart our server, and you're going to very quickly start to see where this performance benefit that you might think that you get by adding in additional children starts to fall by the wayside. So I'm going to save this file. I'm going to kill my server, and then we're going to do this process again. Now, in this case, obviously we have to increase the number of requests that are being issued here. I know that when we increase the number, you're gonna say, Steven, of course it's taking longer. We're adding in more requests. Well, just bear with me. You're gonna see exactly what's going on here in just a second, okay? We will make all the numbers entirely line out. So if you're thinking, Steven, you're increasing the numbers, you're crazy, of course it's gonna take longer. Don't worry, I'm gonna have a very solid answer for you on what's going on. So now this time we have 6 children. So I'm gonna issue 6 requests all at the same exact time. Let's run this and we're gonna see what happens in this case. Okay, I'm gonna run it. Oh, I think I did not restart my server or something. Yeah, I did not restart the server, sorry. So let's try it again. There we go. And now we're gonna wait. Okay, well, what's going on here? How do we interpret this? So take a look. This time around, it took us 3.5 seconds like across the board. So here's my minimum of 3.4 and I've got a maximum of 3.5. So for those 6 requests, just about every single one of them took 3.5. Oops, don't want to show you that yet. Oh, I wanted to do this one over here, sorry. When we start to get the 6 in there, every single one took all the way out to 3.5 seconds. So we're kind of in this situation right here. So let's update this to be now 6, and this was 3.5, like so. So how do we explain this? Well, remember, and this is where, depending on your personal machine, like your laptop or your desktop, you're gonna see slightly different results. I want you to remember that my computer that I'm recording this on right now is a dual core machine. That means that there is an absolute upper limit to my computer's ability to process incoming requests and do some amount of work. And that's not just my machine, right? That's every computer in the whole world. Every computer has some upper limit to the amount of bits and data that it can just crunch at any given point in time. So when we run our code like so, and we do 6 at the same time, that means that in those 6 separate threads that are running in my 6 separate children, we are bouncing between every hash function call at the exact same time. And our CPU is trying to do a little bit of work on this one. and a little bit of work on this one, and this one, and this one, and this one, and this one, all at the exact same time. The result is that we did not get our code executed 6 times faster or anything like that. The result is that it took significantly longer. It took 3.5 seconds to eventually get a response to everyone, excuse me. So although we were able to address all these incoming requests at the same time, the net result was that our overall performance suffered because our CPU was trying to bounce around and process all these different incoming requests at exactly the same time. So this is a very clear case where we have kind of over-allocated instances inside of our cluster. And even though we can definitely start processing all these hashes at the exact same time, which might be good, right? We can start processing everything at the same time and everyone gets a response as fast as possible. The result is that we've kind of created like this big average bottleneck of mediocrity where we can only do so much at any given time, and we've been trying to do too much, so it's slowed down the overall result. So clearly there's an upper bound to the number of children that we might want to create inside of our cluster whenever we have some computationally intensive work to do inside of our application. So let me show you a solution that will work very well here. Now, maybe I'm going to take that back. I'm not going to say it's going to work very well, but I think that you will agree with me that at the end of the day, it's probably a net benefit. So let me show you what I'm going to do. I'm going to go back over to my application. Here's my index.js file. And rather than going totally overboard with my number of forks here, I'm going to go down to just 2 like we had before. So fewer forks, hey, does that mean we're going to run our server more slowly, or what's that really doing for us? Well, let's restart our server and do the benchmark and see what happens. Okay, so I'm going to restart the server. And then I'm going to run the benchmark one more time. Now notice this time I am in fact doing 6 by 6. So like I said before, if you're thinking, Steven, you're doing 6, of course it's going to take longer. This time we're back to just 2 children and I'm doing 6 on both. So let's now give this a shot and see what happens. Okay, feels like we're still waiting for a while. But when we get the result back, you'll notice that we went all the way down to about 3.4 seconds for the longest request. So the longest request was 3.4. But if you really break down what's happening here, you'll notice that our fastest requests were processed in just 1 second. So let's take what we just did and put it into a diagram to give you a better idea. Okay, so here's our new timing. So in this case, we are using clustering and we have just 2 children. But with 2 children, we know that we can only process at best 2 hashes at any given time. Now we are still kind of subject to an overload here, but let's just kind of look at the diagram and see what really happens. Now the diagram itself, just like it was before, it's kind of misleading. All 6 requests technically come in at exactly the same time, right? They all come into our server at exactly time of 0 seconds. But the purpose of this diagram is to show you when the server actually processes at each pbkdf2 function call. So the bars here represent when the CPU is actually working on each hash. So the instant that these first 2 function calls come in, the first 2 calls immediately get redirected over to the CPU. I have a dual core CPU, so each hash is executed on one CPU and gets the absolute full dedicated attention of that one CPU. So the first 2 take from time 0 to 1 second. And after that 1 second, I have already finished the first 2 hashes. Then my 2 running children inside of my cluster say, hey, all right, we've cleared those out. We're ready for the next 2. It goes and grabs the next 2, processes them both in 1 second, and then obviously does the same thing for a 3rd time around. Now, I got a result just a second ago of 3.4. Again, that's because I'm running this video recording software, which kind of exaggerates my results right here. But in the real world, if this was like just me on my laptop with nothing else running, you would have seen 5 and 6 down here run at 3 seconds as well. So even though we have used fewer children, we actually have ended up with arguably a far better performance profile than we did previously. Not only are we finishing all of our hashes more quickly, right? We're doing everything faster than 3.5 seconds, but a bulk of those hashes are being finished significantly faster. So by increasing the number of children that you have inside of your application dramatically beyond the number of actual logical cores that you have or physical CPU cores that you have in your computer, you're going to have a net negative effect on the performance of your system. So the end result of all this, after gabbing away about all this for a super long time on my part, I apologize, but the net result is, what I'm trying to say here is, yes, clustering is great, but you gotta use it in, like, I don't know, don't go overboard with it, right? Don't just think that you're gonna throw 50 children out there and get super awesome performance. In general, you want to match your number of children in your cluster to either the number of physical cores or logical cores that you have. And when I say logical cores, remember that sometimes your CPU your operating system interprets one processor or one core as being like 2. In the case of like multi-threading stuff, in general, I use physical core count, but some of the documentation that you'll see around clustering uses logical cores instead. Using logical cores instead is okay because it does mean that you will handle concurrent requests a little bit better when they are low on CPU requirements. But when it starts to come down to really heavy processing requirement, in general, you kind of want to match up your number of CPUs to your number of children. Just my personal opinion. Okay, so that's been probably way more about clustering than you've ever wanted to know. However, we've still got a pretty basic example here. So let's come back in the next section and we're going to kind of supercharge our clustering setup with an open source project and give you something more production ready to run on your own projects. So quick break and I'll see you in a minute.